Hello and welcome to the second unit of our class, which is going to start with Chapter 5, Exoplanets and the Formation of Planetary Systems. This chapter in the book starts with another example of the Astronomer's Almanac, which is going to tell us about what has been happening with the understanding that we have of planetary systems or solar systems around given stars. And what you should notice is that even though I said that a lot of the very basic physics that we came up with was based on astronomy from hundreds of years ago, we are still learning quite a bit about these planetary systems, even now, even in the last decade or so. And that is going to be meaning that this is a vibrant field. It's not just a field that cut out 500 years ago, but it is one that is still learning and which we can use to learn more about physics, which we can use more about our place in the universe in general. First, we're going to talk a little about the universal makeup of our universe. So stars transform matter from lighter elements into heavier ones. Observations of the spectra of the sun, other stars, and interstellar clouds reveal that hydrogen and helium are by far the most abundant elements in the universe. These two elements account for about 99.9% of all observed atoms. Whereas the Earth, the moon, and most of the other objects that orbit the sun are composed primarily of heavy elements, including, among many others, oxygen, silicon, aluminum, iron, carbon, and calcium. Our current theory about the origin of the universe, or the beginning point of the universe, is called the Big Bang Theory, and according to this, only the lightest elements, hydrogen, helium, and a tiny amount of lithium, were created in the Big Bang. These first elements came into existence as gases. Not all the hydrogen, helium, and lithium that exist today is primordial in origin. Those elements have also been formed by processes occurring inside stars. The first stars, composed only of these three elements, condensed out of the primeval matter about 100 million years after the universe first formed. If planets had also formed back then, they would have been composed of only these three light elements. In a curious alternative use of a common word, astronomers define metals to be all of the elements in the universe other than hydrogen and helium, which, as we said, made up 99.9% of the... Once stars form, gravity compresses and heats the matter in their central core so much that the hydrogen there is transformed into helium in a process called thermonuclear fusion, or fusion for short. Hydrogen fusion has the interesting property that some of the hydrogen's mass is converted into electromagnetic energy, photons, a portion of which eventually leaks out through the star's surface, causing it to shine. This is why the sun shines. Stars also shed matter into space. Some of the heavy elements that formed inside them are eventually ejected into space, along with most of the hydrogen and helium remaining in the outer layers. These ejections occur at different rates, ranging from continuous outflows called stellar winds to the more energetic planetary nebulae, so named because they have not because they have any direct connection to real planets, but because they look like planets as seen through early low-resolution telescopes. Two spectacular detonations called novae and supernovae. Supernovae are such powerful events that fusion continues to occur during these explosions, creating even denser elements than iron that are also expelled from the star. While some supernovae expel their stellar cores, all planetary nebulae and most supernovae leave tiny, dim, but very hot stellar cores, remnants of once mighty stars. Observations reveal that stars form inside interstellar clouds such as Carina Nebula, the Cone Nebula, and the nearby Orion Molecular Cloud. Between a few and a few thousand stars typically form at the same time in these clouds, creating groups called open clusters. It is likely that the solar system formed in such a cluster. Stars in open clusters are not gravitationally bound to each other, and they eventually drift apart, which is why even the closest stars to the solar system are light years away from us today. Under the right conditions, however, fragments of clouds can be forced to collapse and form a star, or more commonly, groups of up to several thousands of stars simultaneously. Wherever a clump of gas is compressed and becomes dense enough so that its own gravity causes it to begin collapsing in on itself, that region has a Jeans instability named after the British physicist Sir James Jeans, who calculated the necessary conditions of gas density and temperature for such collapses in 1902. Pieces of interstellar clouds become Jeans unstable, allowing stars and their hosts of orbiting bodies to form, for at least 3 reasons. First, winds from nearby stars compress gas and dust into the cloud. Second, the explosive force of a nearby nova or supernova compresses regions of gas and dust. Third, pairs of clouds collide and compress each other, each collapsing fragments destined to become a star, or a pair of stars orbiting each other called a binary star system, or even 3 stars orbiting each other called a trinary or a ternary star system. And possibly planets is called a dense core. Just as smoke created in a fireplace swirls as it rises, interstellar clouds are comprised of swirling masses of gas and dust. As a result, many dense cores are rotating as they collapse. Such gas and dust swirls faster and faster as it condenses, forming into protoplanetary disks. The vast majority of the mass of each of these cores' inner regions collapses due to its own gravitational attraction to form 1, 2, or 3 protostars, which are destined to become stars that orbit together. The gas and dust in the disk that is swirling too fast to join the protostars will either remain in orbit and become part of planets, moons, or smaller orbiting debris, or will be heated by energy from the protostars and thereby expelled back into interstellar space. These protostars and protoplanetary disks are shown in this diagram at various rates of their evolution into what will eventually become a planetary system. You can see a cloud in which stars are forming today with your naked eye, namely the middle star in Orion's sword, which looks like a fuzzy blob on the night sky. Called the Orion Nebula or the Great Nebula of Orion, this star is actually an interstellar cloud that is part of a much larger interstellar cloud region called the Orion Molecular Cloud, in which new stars and planets are coming into existence. Most of these protostars that have been discovered are surrounded by protoplanetary disks. These disks are similar to what the solar nebula was believed to have been like more than 4.5 billion years ago. While most protoplanetary disks are relatively uniform, water waves running around them or spiral waves, similar to the shape of a spiral galaxy, these spirals are believed to either result from the gravitational pull of protoplanets there or from some external gravitational disturbance of the disk. In the former case, we may be seeing disks shortly before planets start to form there. Along with disks of gas and dust, large number of comets, orbiting debris composed primarily of rocks and ice, and asteroids, debris composed primarily of rock and metal, have been observed orbiting a few stars. The first system discovered to have comets was the young star Beta Pictoris. Comets outside our solar system are detected as a result of the gas they emit when passing close to their stars, analogous to comet trails we see in our solar system. The first star observed to have asteroids in orbit around it is Zeta Leporis, a young star just 70 light-years from Earth. Although pieces of asteroid debris have not been directly observed in it, their presence has been inferred from the existence of hot, or room temperature, dust. Its asteroid belt, located about the same distance from that star as our asteroid belt is from the Sun, contains an estimated mass 200 times greater than the mass of our asteroid belt. The most likely explanation for this high-temperature dust is that it is being generated by the collision of asteroids. Recall that astronomers believe that gas and dust left over from the formation of a star and its orbiting bodies is expelled into interstellar space by the heat of that star. Therefore, astronomers had expected to find disks of gas and dust orbiting young stars, but unexpectedly they have also found disks of dusty debris orbiting stars as old as the Sun, so they are over 4 billion years old. These stars are all known to have planets, and so the dusty debris surrounding them was perhaps most likely formed by late collisions of asteroids and comets with each other, and perhaps with the planets in these systems. Indirect observational evidence for the existence of exoplanets first came from the observed distortion of protoplanetary disks, where again exoplanets are planets that are beyond our solar system. as I believe I have said in a previous chapter. If one or more exoplanets orbit a protoplanetary disk around a young star, their gravitational pull will affect some of the disk or gas or dust around the star, causing that debris to clump up or warm or become off-center from its star. An example of such warping can be seen in the edge-on disk surrounded by the young star Beta Pictoris, which formed only 20 million years ago. In 2006, astronomers discovered that Beta Pictoris actually has two disks, tilted about with respect to each other. Most of the debris in this is the larger disk seen in further figure. In 2008, an exoplanet denoted Beta Pictoris b was discovered orbiting in the same plane as the smaller disk of debris, indicating that the exoplanet is what holds that disk debris in its tilted orbit. As noted above, Beta Pictoris also has millions of comet nuclei, which were discovered in 2001. By studying such systems as Beta Pictoris, we can begin addressing such questions as whether Earth may have acquired its water from comets in the young solar system. We will use the remainder of this lecture to talk about other different ways that exoplanets are detected using scientific methods. First is the transit photometry method, whereas observing distorted protoplanetary disks was one of the first methods of discovering exoplanets. The most successful method has been to look for exoplanets that block some of their star's light as the exoplanet transits between its star and Earth. If these systems, the disks have already dissipated. Because the exoplanets that transit are not located between us and the stars they orbit for very long, using this technique requires watching a fixed set of stars continuously over a period of years for brightness variations caused by transit. NASA's Kepler Space Telescope, which operated at full capacity between 2009 and 2013, is to date the most successful collector of transit photometry. It stared continuously at about 150,000 stars, continually recording their brightness. When exoplanets passed between one of these stars, the star's brightness dipped. Next is the radial velocity method. When a massive exoplanet is orbiting close to its star, their center of mass is not the star's center. As a result, if the exoplanet has any motion towards and then away from us in its orbit, so too does the star. We can detect this motion through the Doppler shift of the star spectrum. The length of time of one cycle of Doppler shifts towards us, then away from us, then back to start is the period of that exoplanet's orbit. Modern spectroscopic techniques are so good that we can detect stars approaching or receding at speeds as low as some number which unfortunately got deleted. Because the motion of the star toward or away from us is called its radial motion, this technique is commonly called the radial velocity method of detecting exoplanets. Thanks to their large masses and small orbits, gas giants called hot Jupiters are the easiest class of exoplanets to detect using the radial velocity method, and as a result, they were the first to be detected in this way. Just as the moon goes through a cycle of phases as seen from the Earth, we can potentially see exoplanets go through cycles of phases as they orbit their stars. Unlike the moon, which we can see separately from the sun except during a solar eclipse, exoplanets that go through measurable phase cycles as seen on Earth are too close to their stars for technology to yet be able to see them separately. Rather, we see the combined star-exoplanet system change brightness. The exoplanets Kepler-70b and c, orbiting very close to the star Kepler-70, were the first exoplanets discovered by this method in 2011. Next is variable transit timing. When a star has only one exoplanet, and that exoplanet transits in front of the star, the interval between transits is always the same. However, if there is more than one exoplanet, the gravitational pull of the others on this one that transits will cause the interval between the transits to vary. That occurs because the different exoplanets have different orbital periods, and so their locations vary relative to each other. This causes their gravitational interactions to vary from orbit to orbit, therefore changing the timing and precisely when a transit seen from Earth occurs. The changes in the transit can be used in calculations to determine the masses of these exoplanets. Transit duration time variation. In a method related to variable transit timing, the transit times of some exoplanets vary from one orbit to the next. This is caused by gravitational interactions, often between the exoplanet and one or more of its moons. Keeping in mind the exoplanet's motion around the center of mass of its moon, the exoplanet can be on different sides of the planet-moon, depending center of mass when it transits as seen from Earth. Depending on when it is relative to the center of mass, the exoplanet will be moving across the celestial sphere at different speeds, thereby changing how long it takes to transit. Next is eclipsing binary minima variation. The presence of exoplanets in binary star systems can measurably affect the orbits of the stars. In this scenario, the stars eclipse each other as seen from Earth. If the two stars are not identical in color and brightness, astronomers can determine which one is eclipsing the other. In this approach to locating exoplanets, an exoplanet in an eclipsing binary star system may have enough mass or be close enough to one of the stars to measurably affect the location of the center of mass of the entire system. In such cases, the periods between eclipses are affected by the center of mass motion in analogy to the effect that causes transit duration and time variation discussed above. The presence of the exoplanet Kepler-16b was confirmed by its effects on the two stars it orbits. Next is the astrometric method. The radial velocity method uses the fact that many exoplanets can make their stars periodically move towards and then away from us. Many exoplanets can also make their stars appear to wobble on the celestial sphere. This occurs when exoplanets orbit the stars in a complement of their motion perpendicular to our line of sight. That is, some of their motion is on the celestial sphere. This is analogous to the motion you would see if you put your arm straight out in front of you and watch your hand as you move your arm side to side or up and down. The stars orbiting with these exoplanets move around their common centers of mass with motion that appears to be moving back and forth on the celestial sphere. In 2009, the Hubble Space Telescope imaged the wobble of the star Gliese 876, revealing the presence of a previously undetected exoplanet orbiting it. Several other exoplanets had already been detected orbiting it using the radial velocity method. Then there's the direct imaging method. We cannot yet resolve most of the exoplanets we have detected. Direct imaging is extremely challenging because even planets like Jupiter, which scatter most of the light that strikes them, are very dim compared to the stars they orbit. In order to be classified as a star, an object has to have sufficient mass to compress its insides enough to force fusion to occur at its core. The lowest mass for this can be about 0.08 solar masses, which is equal to about 75 masses of Jupiter. Because stars are so bright, the first direct image of an exoplanet was made in a system where the exoplanet is orbiting a much dimmer object than a star, called a brown dwarf. Brown dwarfs have masses between 13 and 75 masses of Jupiter, so they are not fusing hydrogen into helium. Therefore, they are much cooler and dimmer than actual stars. That first exoplanet orbiting a brown dwarf was directly imaged in 2004. Labeled 2M1207b, this exoplanet orbiting a brown dwarf labeled 2M1207, which has only 0.025 solar masses or 26 masses of Jupiter. Next is the microlensing method. In 2004, astronomers began finding exoplanets by using a property of space that Albert Einstein discovered. His theory of general relativity, introduced in Chapter 3 and explored in detail in Chapter 15, shows that matter warps its surrounding space, causing, among other effects, passing light to change direction. This phenomenon is quite analogous to how light passing through a lens changes direction and is focused. Light can also be focused by gravity. In the case of stars and planets causing it, the effect is called microlensing or gravitational microlensing. Figure 511 on the next slide shows how a star with an exoplanet passing between Earth and a distant star can focus the light from the distant star, causing it to appear to change brightness. This change occurs twice, once as the distant star's light is focused towards us by the closer star, and again to a larger extent when the light is focused towards us by the exoplanet and the star together. This is seen here as there is, in the first diagram, there no lensing, or there is no bending of the light. However, as the sun passes close to the light, it causes a bending, which causes there to be a magnification of the light coming from the distant source. And as the star passes by both the exoplanet and the star, there is an even greater bending in the third diagram. The pulsar timing method. One of the rarest methods for detecting exoplanets is their influence on the remnants of stars. As all stars evolve, meaning that their chemistry, size, temperature, and other properties will change over time. Eventually, they stop fusing and either explode or simply die out. Stars initially between 8 and 25 solar masses explode as powerful supernovae and leave cores of between 1.4 and 3 solar masses, compared to composed nearly entirely of neutrons. Many of these neutron stars are rotating hundreds of thousands of times a second, and like the Sun, they have magnetic fields that whip around with the rotation of the neutron star. These whirling magnetic fields generate pulses of radio waves, visible light, and other radiation. Hence, they are called pulsars. If we are in the line of sight of the pulses that we see them, isolated pulsars emit among the most regular pulses that we have ever detected, far more precise, for example, than the most accurate wristwatch. If a pulsar has exoplanets orbiting it, then the motion of the pulsar around the center of mass of the exoplanet pulsar systems can be detected by the changes in the timing of the pulses. Despite the fact that pulsars are extremely rare compared to stars that are still shining by fusion, the first exoplanets ever discovered were found because of their effects on pulsar timing. 2 exoplanets were detected orbiting the pulsar PSR B125 plus 12 in 1992, and a third was detected in its orbit in 1994. The oldest known exoplanet, PSR B162026b, was discovered orbiting a pulsar and white dwarf pair 12,400 light years from Earth. The exoplanet and its host stars were about 12.7 billion years old, meaning that this exoplanet was formed only a billion years after. While there are different planets and different exoplanets orbiting around the stars, and we have found quite a few of them, most of them are not going to be in a temperature that we ourselves as humans would be comfortable with. Depending on the size of the star, the distance from the coldest that humans can inhabit to the hottest that humans can inhabit is called the Goldilocks zone, and it varies depending on the size of the star. As we have seen, there are several methods for detecting exoplanets, and some of them are diagrammed here for clarity. And because there are so many methods and so many different types of exoplanets, there are a bunch of different properties of the exoplanets which can be determined the same way that we determine the properties of stars through telescopes and spectroscopy. These are not going to be covered in the lecture but are in the book, as the main ideal is just that there are a ton of different ways that you can put matter together and have different sizes of exoplanets, and we are finding that they are very, very varied in their composition and their properties.